Free energy and thermodynamics. Now, the first law of thermodynamics says that energy can neither be created nor destroyed in chemical processes. The total mass and energy of the universe cannot change. It's a constant, although you can transfer energy from one place to another. And since you can't create energy, merely move it around, you can't win. So the first law is all about conservation of energy in chemical processes. And for an exothermic reaction, heat lost from the system goes into the surroundings. Two ways energy is lost from the system. It's converted into heat or used to do work. Energy conservation requires that energy change in the system is equal to the heat released plus the work done. The change in energy equals Q plus W, where Q is the heat involved, W is the work done. Sometimes it's expressed this way as a change in enthalpy plus constant pressure times the change in volume. And delta E is a state function. And that means that the internal energy change is independent of how it's done. The change in energy is equal to the energy of the final state minus the energy of the initial state. The path of getting from one to the other is not considered. So thermodynamics considers the initial energy state and the final energy state, but does not take into account how it moves from the initial state to the final state. That's studied in kinetics, where you look at intermediate states and the speed of a reaction. But in this chapter, we're not going to focus on the first law of thermodynamics. We're going to focus on the second law, the energy tax. You know, the first law, as we said, kind of boils down to you can't win, at least in terms of energy. The second law of thermodynamics says that you can't even break even in terms of energy. To recharge a battery with 100 kilojoules of useful energy, it will require more than 100 kilojoules to do the job because of the energy tax. If you want to light up a room, you might input 100 watts of electrical energy, but only 5 watts is actually being converted into light. 95 watts of energy is being converted to heat in the process. Of course, the new LED bulbs are much more efficient than the old-style incandescent bulbs. Every energy transition results in a loss of energy, and conversion of energy to heat results in heat lost to the surroundings. Formally, the second law says, for any spontaneous process, the entropy of the universe increases. Now let's take a look at the energy efficiencies involved with heating your house with natural gas versus electricity. If you burn natural gas, there is a heat tax as heat escapes through the chimney, but it's a relatively efficient process. If you're using electricity to heat your home, every step in the process involves a loss of heat, a heat tax. You burn the fossil fuel, there's a heat tax there. You use the energy to make steam, there's a heat tax there. You use the steam to turn a generator, there's a heat tax there. You transmit the electricity from the power station to your home, there's an energy tax there. And then you use the electricity to power the electrical heater in your home, there's a heat tax there. The fewer the steps generally results in a lower total heat tax. The second law of thermodynamics also denies the possibility of perpetual motion machines. Here you have one that seems to work until you look behind it to see the motor that's powering it. This is called the unbalanced wheel, and there have been a variety of these throughout history, but none of them take into account the fact that air resistance and friction are eventually going to stop the motion. I found these on YouTube, annoyed that some seem to claim they can do it. I really liked the explanation by Tom Scott in the video Wheels, Bombs, and Perpetual Motion Machines. You should check it out. Back in the day, I had to have my shot at discussing the concept of entropy, and I came up with this. Check out the video called The Entropist on YouTube. To understand entropy, it helps if we understand the nature of spontaneous versus non-spontaneous change. For example, we know it's spontaneous that a balloon deflates, releasing helium gas to the atmosphere. And we know it's virtually unheard of for helium gas to spontaneously flow back from the atmosphere and fill up a balloon. It's just not done. Likewise, once we ignite a newspaper, we expect it to spontaneously burn to form carbon dioxide, water, and ash. We never see carbon dioxide, water, and ash spontaneously reforming a newspaper. To help us understand why, let's examine the concept of spontaneity in terms of probabilities. For example, in poker, 3 of a kind is not as valuable as 4 of a kind, which in turn is not as valuable as a straight flush, which in turn is not as valuable as a royal straight flush. That's because in terms of probability of the cards that are dealt, 3 of a kind is more probable than 4 of a kind, etc. A royal straight flush is very improbable and therefore considered more valuable. Now let's relate this idea of probability to molecules. In states A, B, and C, we consider the external arrangement of 4 atoms. A through C are called macrostates. In state A, we have 4 particles on one side of the container. In state B, 4 on the other side. And in state C, we have 2 and 2. But if we were to number the atoms 1 through 4, we can consider their individual positions in each state. These internal arrangements are called microstates. Let's start with the last macrostate, state C. This macrostate can be achieved through several different arrangements of the particles. We can have numbers 1 and 2 on one side and 3 and 4 on the other, 2 and 3 on one side and 1 and 4 on the other, etc. So there are 6 different particle arrangements that result in the same macrostate. There's only one possible arrangement that gives state A and one that gives state B, but there are 6 possible arrangements that give state C. Therefore, state C has higher entropy than either state A or state B. The macrostate with the highest entropy also has the greatest dispersal of energy. At first it was thought that the enthalpy of a process, the heat involved in a chemical change, determined spontaneity, where an exothermic change led to a spontaneous result. But some processes are spontaneous, but endothermic. Ice melting above 0 degrees is spontaneous, but endothermic. Water evaporating is spontaneous, but endothermic. And ammonium chloride dissolving in water is spontaneous, but endothermic. So let's take a look at the case of ice melting. In which state, solid ice or liquid water, are particles more random and energy more dispersed? In ice, A, or in liquid water, B? Well, the particles in ice are locked in a crystal array. That's why ice is solid. But in liquid water, the particles are moving around, making and breaking temporary attractions with each other. So when ice melts, there's increasing entropy. Energy is more dispersed in liquid water than in solid ice. How about water evaporating? In which state are particles more random and energy more dispersed? In water vapor, the water molecules are in the gaseous state, very far apart, moving independently through space. In liquid water, the particles are making and breaking attractions with one another. So when water evaporates, there's increasing entropy and energy is more dispersed. How about sodium chloride dissolving? In which state are particles more randomized and energy is more dispersed? Solid salt or salt in the solution state? In solid salt, the sodium and chloride particles are locked into a crystal array. When they dissolve, they're pulled out of the array, each surrounded by water molecules. Therefore, entropy is increasing as sodium chloride dissolves. Why does it require energy to have a tidy room? Why is a messy room more spontaneous? Well, if you think about it, in order to have a tidy room, Each one of your belongings need to be put away in a limited number of defined spaces so that the room can be considered tidy. But there are almost an infinite number of possibilities for each item to be placed such that the room is considered messy. There are many more positions available for all of your items to have a messy room instead of a tidy room. If we look at the actual equation that defines entropy, entropy is equal to K times the natural log of W, where K is Boltzmann's constant and W is the number of energetically equivalent ways that the particles or items can be stored. Random systems require less energy than ordered systems. That's why you have to put energy into your room so that it will be defined as tidy. Any spontaneous process is irreversible. It will proceed in only one direction. A reversible process, on the other hand, will proceed back and forth between two end conditions, with no net change occurring once dynamic equilibrium has been reached. If a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. Above 0 degrees, is this going to be spontaneous or reversible, ice melting? And of course we know ice melts spontaneously above 0 degrees. Now what about at 0 degrees? Is it spontaneous or reversible? Here it's reversible at 0 degrees, and there can be an equilibrium reached between ice crystals and liquid water molecules. What about below 0 degrees? Here we know water is going to freeze into ice crystals spontaneously. So the second law of thermodynamics says that the total entropy change of the universe must be positive for a process to be spontaneous. For a reversible process, there will be no change to the total entropy of the universe. For irreversible or spontaneous processes, the change in entropy of the universe must be greater than 0. And the change in entropy of the universe is equal to the change in entropy of a system plus the change in entropy of everywhere not defined as the system, the change in entropy of the surroundings. For a spontaneous change, if the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount, such that the delta S of the universe is positive. The increase in delta S of the surroundings often comes from the heat released in an exothermic reaction. Heat is going to increase the entropy of the surroundings. So how do we measure entropy? Well, we use the third law of thermodynamics, which says that a perfect crystal has 0 entropy at absolute 0. Therefore, you see, entropy measurement is based on an absolute, not a relative scale. Unlike enthalpy, which is based on a relative scale, more on that in a second, we use standard molar entropy, S0, with units of joules per mole K. Now, what does the little 0 mean that you see on the symbol for entropy or enthalpy? It indicates standard state in thermodynamics, that is 25 degrees Celsius and 1 atmosphere of pressure. And don't confuse standard state with standard conditions of temperature and pressure, STP conditions for gases. They're not the same. Now take a look here. All of the elements and compounds in this chart have an entropy value on them, whereas there's only an enthalpy value for compounds and for elements which are not in their standard state. Carbon exists as two allotropes, diamond and graphite. The most stable one is graphite, and the reference enthalpy for the element graphite at standard state conditions is 0, just like it is for all of the other elements that you see here. If they're in their standard state of 25 degrees Celsius and 1 atmosphere, their reference enthalpy is 0. Now, when they combine to form compounds, that's how you calculate the enthalpy of a compound. You measure the heat evolved when elements combine to form compounds, like hydrogen and oxygen to form water, and that becomes the enthalpy of formation of the compound. Now let's consider entropy and phase. As one moves from solid to liquid to gas, the degrees of freedom of motion increase. There are more macrostates and therefore higher entropy. Take a look here at the entropy of liquid water, which is 70 joules per mole Kelvin, versus the entropy of gaseous water or water vapor, 188.8 joules per mole Kelvin. Let's consider the entropy change when dissolving. Usually, more degrees of freedom are available in the dissolved state compared to the solid state. There are more macrostates and therefore higher entropy. Consider sodium chloride solid versus sodium chloride dissolved in water. There are a couple of exceptions, though. Aluminum salts can have a net decrease in entropy when dissolved due to strong hydration. And all gases have lower entropy when dissolved. As gases, there are many, many degrees of freedom not found in the solution state. Entropy and molar mass. The larger the molar mass, the larger the entropy. And it's because there are available energy states that are more closely spaced in particles that have larger molar mass, therefore allowing more dispersal of energy through the states. Also, relative standard entropies involving molecular complexity. The larger, more complex molecules generally have larger entropy. Compare argon, which is a simple atom. Molar mass is 40, entropy 154.8. Nitric oxide, molar mass 30. Molar mass is smaller, but the entropy is higher because it has a more complex structure to the molecule. More available energy states, therefore, are available, allowing more dispersal of energy through the states. Calculating the change in entropy for the system for a change of state. Because a phase change is a reversible process, one can calculate the entropy change of the system from the enthalpy of the phase change. That's the heat of fusion or heat of vaporization. And the equation is very simple. The change in entropy of the system equals the heat of fusion divided by the absolute temperature of the phase change, or the change in enthalpy of vaporization, heat of vaporization divided by the absolute temperature of the phase change. There's a caveat which we will talk about in a little bit. If not a reversible process like a phase change, one can use the same equation to calculate the entropy change of the surroundings from the enthalpy change of the system. So we'll talk about that in a little bit, but for right now, for a phase change, you can calculate the change in entropy of the system. So here's a sample problem. Calculate the change in entropy that occurs in the system when 4.8 moles of diethyl ether condenses from a gas to a liquid at its normal boiling point of 34.6 degrees Celsius. And the heat of vaporization is 26.5 kilojoules per mole. Turn your playback off, see if you can calculate it, and then come back and we'll show you my calculation. All right, here we go. Did you end up with 414 joules per Kelvin? One mistake you might have made is if you didn't convert the enthalpy given as kilojoules per mole into joules per mole, because entropy is usually joules per mole. So you'd have to multiply 26.5 by 1,000 to get the heat of vaporization as 26,500 joules per mole divided by the absolute temperature.